This time we're going to talk about adenosine triphosphate, or ATP. Last time we knew that there is something called energy coupling, and there's a type of energy coupling between different reactions which is called indirect energy coupling, and the other one is of course direct energy coupling. And regarding the indirect energy coupling, we knew that there could be two chemical reactions with inputs and products, or reactants and products, and these chemical reactions are related to each other through a molecule that changes its structure, and during that change energy is released so that it could provide the reactions with the sufficient energy. And this is how these two reactions would be linked or connected to each other. And so this kind of molecules are called macroergic compounds. Macroergic compounds. And the most important macroergic compound is the universal energy currency, which is ATP, or adenosine triphosphate. So why is it that way? What does ATP do in order to release energy and supply the chemical reactions with the sufficient energy? The first thing that we need to know is the structure of ATP. So the structure of ATP looks like this. So here we have the adenosine part, which is this part. This is adenosine. And here we have the 5-carbon ring of ribose. And then we have phosphoric acid groups. So a phosphoric acid group consists of 4 oxygen atoms and a phosphorus atom. So it looks like that. And one of the oxygen atoms has a double bond, and we will know why in a moment. So we have 3 of these. So we have another phosphorus atom, and then the third one, and again this one is double bonded, O, and then double bond, and then O. These free oxygens here would have negative charges, and the reason why this part of the compound contains a lot of energy is that it is resonance stabilized. Resonance stabilized. What does it mean, resonance stabilized? We have to know that some chemical compounds are energy stable and some other chemical compounds are energy unstable. An energy unstable compound would directly break down because the formation of bonds is way too hard, because it needs a lot of energy, and if the compound is unstable, it will not sustain this high amount of energy needed and it will break down. On the contrary, our compound here is energy stable through resonance. So the point is Here we have 4 oxygen atoms. As simple as it could be, we should know that this double bond doesn't stay there on just one oxygen atom. It actually moves, so sometimes it's here, sometimes it's there, sometimes it's there, and sometimes it's there. So it's actually moving all the way because this is a chemical compound and there is an electron cloud throughout the surrounding the whole oxygen atoms, and the valency electrons of oxygen, which are depicted by this minus here, actually move from one oxygen atom to the other. So it's not fixed like that. But we would like to keep the double bond right here. This motion of the atoms and the change of the position of the double bond and the valency electrons together is called resonance, as simple as it is. And so by this, actually the compound is stable. It's in a stable state. And in order to break any of these bonds, you would need a very, very high amount of energy to be produced after this action.